Okay, so in this video cast, we'll take a look at weak acids and the consequences of those dissolving in water to find pH, POH, H+, and OH- ion concentrations in these solutions. Remember, last video cast we looked only at strong acids and strong bases, and those had a single arrow, meaning that when they dissolved, they completely dissociated, and we could find directly the H+ or the OH- ion concentration. With weak acids or weak bases, in this case we're only going to look at weak acids, we have to take a look at the equilibrium constant and how much is created on the product side of the reaction in terms of H3O+ or in terms of OH- to determine the pH. Remember that weak acids are everything else besides the acids that you memorized. Remember Heiber, Hickel, high, that whole term thing? Those are the strong ones. Anything else that you encounter, always assume is a weak acid. So, first question is, what does Ka mean? Well, if we have a weak acid, we'll call it Ha, just to make one up, and we react it with water, it is going to give away a proton. And it's going to give away a proton to the H2O, and it's going to form some H3O+ and some A-. And if we write the equilibrium constant expression for this, K is going to equal H3O+ times A- divided by HA. And we're going to leave water out of that because remember, water is a pure liquid and always leave pure liquids and solids out of the equilibrium constant expression. Since this is an equilibrium constant for an acid, we're going to rename this not Kc anymore, or Kp in terms of pressures or concentrations. We're going to call it K sub A. A meaning for an acid. And remember, it's the hydronium ion concentration times the anion that was attached to the acid divided by the original or the concentration of the acid at equilibrium. So, first question. A solution of formic acid is found to have a pH of 2.38. Calculate the Ka. Calculate the Ka. So, first thing to do is to write down the equation, HCHO2, and then we'll react that with some water. And then what we're going to do is we're going to have the acid give away its proton, and we'll form some H3O+, and then we're going to have some CHO2-, and set up an ice table. Initial, change, equilibrium. Now, the one thing that is mixed up on my paper, which is hopefully fixed by the time you get it, is that it doesn't tell you the original concentration of the formic acid solution. And if you look in your textbook, or you hopefully look on your example page, is that it should say that it is an original concentration of 0.1 molar. At least that's what we're going to go with for this example problem. So we can fill this in as it's 0.1 molar to start with. We don't care about the concentration of water because it's not going to go in our equilibrium constant. It's a pure liquid, so you could just put dashes down there for the water right away. And originally we don't have any of this or any of this because none of it's dissociated. Okay? Now it tells us that the pH is 2.38. And remember, from the pH we can find three different things. We can find the H+ ion concentration, we can find the OH- ion concentration, and we can find the POH. The thing that would be valuable to us here, though, is to find the H+ ion concentration. Because remember, H+ ion concentration and H3O+ ion concentration are the same thing. And so to find the H+ ion concentration, what I'd do is take my 10 to the x key on my calculator and take 10 to the negative 2.38, which is the pH. And if I do that on my calculator, I end up with an H+ ion concentration of 4.17 times 10 to the negative third. And this is how much I'll gain of H3O+, or that will be my change on this side of the reaction. And since it's a 1-to-1 ratio here, this is how much HCHO2 I will lose, 4.17 times 10 to the negative third. Since it's a 1-to-1 ratio here of the H3O and the anion, I'll also gain 4.17 times 10 to the negative third here. And then I can fill in the rest of my table. This will end up being 4.17 times 10 to the negative third, this too, and then this one right here will be 0.1 minus 4.17 times 10 to the negative third. Now if you do this on your calculator, if you do 0.1 minus 4.17 times 10 to the negative third, let's just do it so then you can see it actually. 0.1 minus 4.17 times 10 to the negative third, I end up with 0.0958. And if I were a rounding person, I could round, it's 5 or more rounded up, I could round it up to 0.01 or pretty close to what point 0.1, right? 9 here could round it up to 0.1, which is pretty close to what I started with. So in other words, when I subtract these, I'm really going to end up with like 0.99 or so, which is, I'm sorry, 0.095, which is pretty darn close to 0.1. Hey, this makes it really handy because then I can actually kind of ignore this amount right here. It's going to end up being about 0.1 once again. I'm not losing very much. The equilibrium is weak, meaning there's not a whole lot of this made. Why does this make a difference? Well, then when I find the Ka expression would be 4.17 times 10 to the negative third times 4.17 times 10 to the negative third. Multiply those two together and then divide it by my concentration, 0.1. And remember, actually it's like 0.095, but I'm going to round that to be just about 0.1 here again. And if I plunk that into my calculator, I end up with a Ka equal to 1.8 times 10 to the negative fourth. And if you look in the back of your book, Appendix C, they have lots of Kas listed for a number of different acids. And this is pretty darn close to what it actually is. Next, it says calculate the percentage of acid ionized in this 0.1 molar solution. Well, percent ionization is equal to the H plus ion concentration at equilibrium divided by the original concentration of the acid. The original concentration or initial concentration of the acid times 100%. And here in this one we had 4.17 times 10 to the negative third being our concentration of H plus. And then we'll divide that by, that's the equilibrium concentration, I'm sorry if I said that wrong. The equilibrium concentration divided by the original, which is 0.1 molar, and then multiply by 100%. And if you do that, you end up with a percent ionization of about 4.2. So it's about 4.2% ionized. The magic number in percent ionization is 5. And we'll find out why that is in just a little while. If it's 5 or less, then you can do this, you can do a lot of fancy things as far as ignoring some things that make your math a lot easier. Going on, part 2. Niacin, one of the B vitamins, looks like the figure to the right, and you can see here is the actual niacin molecule, and it's kind of neat to see something like this. This a hexagon-shaped thing actually means that there's carbon atoms at each corner right here, and each carbon is also filled with hydrogen atoms to make sure that it ends up with 4 bonds. So it'd have 2 hydrogens around each one. So if you ever see one of these hexagon-shaped things, you always think, oh yeah, it's a ring of carbon atoms. The thing that makes it acidic, though, is this OH bond right here. This hydrogen is the acidic hydrogen that can be cleaved off and therefore donated to something else. Anyway, the B vitamin is actually an acid, so if you take a supplement, or if you ever eat B vitamins, which you all do, you can say, hey, I'm eating something quite acidic. Well, it's actually not a very strong acid at all. It turns out that there's a 0.02 molar solution, and it has a certain pH. What is the percentage of the acid that's ionized? To find the percent ionization, remember, what you do is you take your H plus ion concentration at equilibrium, which we could find from the pH right here, and divide it by our initial concentration, which is 0.02 molar. So to find our H plus ion concentration at equilibrium, we'll take our calculator and we'll do the 10 to the x key right here. So second, 10 to the x. That puts 10 to the caret, and then type in negative 3.26, hit enter, and it turns out to be about 5.5 times 10 to the negative fourth. So 5.5 times 10 to the negative fourth is the equilibrium concentration of H plus divided by 0.02 times 100%, and our percent ionization for this turns out to be about 2.7% ionized. So if they give you the pH, you can go right to the H plus, and of course since you know the original concentration, you can find the percent ionization pretty quick. Next it says, what is the acid dissociation constant for Ka of niacin? This is similar to the problem that we did above, where to find the Ka, what we'd need to know is the concentration of the H plus times the concentration of the anion divided by the concentration of the acid, all at equilibrium. So best way to do this, once again, is to set up an ice table, write an equation and set up an ice table. And I'll write this kind of over here on this side where you can see it a little bit better. We'll just write the acid of niacin as H, and then I'll write down niacin right here, okay? Because this is the anion right here. And then we're going to react it with some water. And then when we do this, it will form H3O plus, and it will also form the niacin anion right here. And I'll just write it as NiAC rather than writing this whole thing right here down. Sometimes it's just easy to kind of abbreviate what the chunk of the acid is. And then we just look at the interesting thing, which is the H3O plus. Set up an ice table. Put in your initial value right here, which is 0.02 molar. And then we can put in nothing, nothing, nothing to start with. And then we know from our calculation up above that the equilibrium concentration of H plus is 5.5 times 10 to the negative fourth. So we'll put at equilibrium 5.5 times 10 to the negative fourth here. You can see that these are a 1-to-1 ratio, so this is 5.5 times 10 to the negative fourth as well. Niacin would be 0.02 minus the 5.5 times 10 to the negative fourth, but this number is going to be extremely small compared to the 0.02, so I'm going to end up with 0.02 here once again. And to find the Ka, we take these two multiplied together, divided by 0.02, because it's these two concentrations divided by the Ha, and we end up with a Ka for niacin of 1.5 times 10 to the negative fifth. 1.5 times 10 to the negative fifth. We'll actually use that in the next problem. What is the pH of a 0.01 molar solution of niacin? Well, now it's asking us to find the pH. So the goal here is to find out what is the H3O plus ion concentration, because if we find the H3O plus ion concentration, we just take the negative logarithm of that, and then we've got the pH. So write the equation again. H niacin plus water, and double arrow because it's a weak acid, and we're going to end up with some H3O plus, the thing of interest, and then our niacin anion right here. Initial change equilibrium. Initially we have a 0.01 molar solution now. The water we don't care about because that's just a pure liquid and it's not in the equilibrium expression already. The H3O plus, there's none of it and none of the niacin anion to start with. But now we're not given what the final pH is, we're asked what it is. So we have to go back to chapter 15 and use a variable for these, saying I'm going to lose X amount of this, I will gain X amount of this, and gain X amount of the niacin, and I'll end up at equilibrium with 0.01 minus X, X amount of this, and X amount of this. And if I write the equilibrium constant expression, it'll be these two multiplied together divided by 0.01 minus X. So writing it in terms of X, Ka for this will equal 1.5 times 10 to the negative fifth. Remember, I found that in the last problem, which is equal to X times X divided by 0.01 minus X. Now you're looking at it and you're saying, oh boy, now I've got to collect the X terms. I'm going to end up with an X squared and an X times 0.01 or something, and I'm going to have to solve a quadratic equation. And that's absolutely fine if you want to do that. But one of the cool things about knowing the percent ionization is less than 5% is that you can take this X right here and you can ignore it, because you know that it's going to be small compared to the 0.01 molar or the original concentration. Now, we'll find out that occasionally you can't ignore this x, and you will end up solving a quadratic equation, but there's never been one in the history of the AP exam that you actually have to solve it. You just have to know that, hey, I can usually ignore this, except if the percent ionization is too high. General rule is called the 5% rule, 5% or more. And so it's valuable to find the percent ionization every time you do this. So if we take this and ignore this x, and we say it's small compared to 0.01, now it becomes a super easy problem to solve, because it's x squared over 0.1 is equal to 1.5 times 10 to the negative fifth. Hey, multiply both sides by 0.1. This goes away, square root the animal, and you end up with x, which remember is equal to the H3O plus ion concentration. Remember, we called x right here H3O plus ion concentration, and that turns out to be a concentration of 3.87 times 10 to the negative fourth. And if you take the negative logarithm of that, then of course you have the pH, and if you do that, it turns out the pH is 3.41. 3.41. Now, if you wanted to make sure that you could ignore this x and make sure that it was small, you'd go through and you'd find the percent ionization for it. If it's less than 5%, that's okay. Let's go on to the next problem, though. Let's do one where it is actually illegal to ignore this x, so then you can see how that kind of works out. Let's do letter B right here. Well, A actually has us find the percent ionization of that, so let's go ahead and do it just so we remember how to do it once again. Percent ionization, remember, is equal to the H plus ion concentration, which we just calculated was 3.87 times 10 to the negative fourth, and then divide it by the original, which is 0.01, times 100%, and if you calculate that, it turns out to be 3.87% ionized, or about 4% ionized, which means it's okay to make that assumption that the x is small. If it's larger than 5%, that means it's not okay. Let's do letter B and let's see how that turns out. And I'm going to do it on a separate piece of paper, so we've got a little bit of extra room here. This one says now, calculate the percent of niacin molecules that are ionized. So we have to do the entire problem where we take H, niacin, react it with water, end up with some H3O plus and some niacin minus right here, initial change equilibrium. It tells us that this starts as 1 times 10 to the negative third. None of this, none of this, none of this. Ignore, ignore. The water, we're going to lose x of this, gain x, 1.0 times 10 to the negative third minus x. This is x, this is x. And so it ends up being these guys, x times x, or I'll just write it as x squared, divided by 1 times 10 to the negative third minus x is equal to Ka, which we solved for before, and that was 1.5 times 10 to the negative fifth. Now let's ignore it. Ignore the x. Solve for x squared, and it turns out in this case that x equals 1.22 times 10 to the negative fourth. 1.22 times 10 to the negative fourth. This is our H plus ion concentration when we ignore this x. But the question, remember, asked us for the percentage ionization, and the percentage ionization will tell us, was it okay to do this ignoring of x? Was it okay to do this ignoring? Well, to do this, remember, we take the H plus ion concentration at equilibrium and divide it by the original concentration, which remember was 1 times 10 to the negative third molar. So if we take these guys and I put in 1.22 times 10 to the negative fourth divided by 1 times 10 to the negative third and multiply by 100%, it turns out to be 12.2%. Uh-oh, we're over 5%, which means, bad news, you got to go back to this equation. You cannot ignore this x. You need to solve it for this x using the quadratic equation, and you'll end up with the more correct concentration of H+, and therefore the more correct pH if they're asking you to find that. Remember, you only need to do it if the percentage ionization is greater than 5, and generally on the AP exam there's never been a question where you actually have to solve the quadratic equation like this. You just need to state that the reason I can ignore this is because it's small compared to the original concentration, small compared to this original concentration, and I'm going to make that assumption. And if it turns out to be wrong and it's too big, you need to explain why I need to go back and do it.